Some nights the sky holds a kind of stillness that feels almost deliberate, as if the universe itself has paused just slightly to let you breathe. If this feels like a good place to rest tonight, you are welcome to stay. Now, let's drift. There is something out there among the galaxies that has been quietly puzzling astronomers for a long time now. Not a mystery that announces itself loudly, not the kind of discovery that arrives with urgency or alarm. It is softer than that, more like a gradual realization, the kind that comes when you look at something familiar for long enough and notice very gently that something about it does not quite fit. Galaxies are the largest structures in the visible universe, each one a vast, slowly turning collection of stars, gas dust, and something else, something we cannot see, but can feel in the way things move. Some galaxies are spirals arms curling outward like slow whirls of light. Others are elliptical, round and smooth and ancient, shaped like enormous glowing stones worn soft by time. And some are irregular, no clean shape at all, just scattered light as if something long ago disrupted the pattern and the galaxy never quite returned to order. For most of the history of astronomy, scientists looked at these shapes and saw what they expected. Structure, order, the quiet obedience of gravity. Stars pull on stars, galaxies pull on galaxies, and everything arranges itself into forms that mathematics can describe, and for a long time that was enough. But then slowly researchers began to notice the places where the mathematics didn't quite hold. It began as many quiet revolutions do, not with a dramatic announcement, but with a number that would not behave. An astronomer named Vera Rubin, working in the latter half of the 20th century, was measuring how fast stars move within spiral galaxies. It was meticulous work, patient work, the kind of science that asks you to look carefully at something ordinary and trust that it will eventually tell you something true. What she found, though, was not ordinary. Stars at the outer edges of spiral galaxies far from the dense bright core were moving far too fast. In a well-behaved galaxy governed by the gravity of all its visible matter, those outer stars should slow down, with distance the way planets farther from the Sun move more slowly in their orbits. It is a clean, predictable relationship, one that holds everywhere else in physics. But in galaxy after galaxy, the outer stars refused to slow. They kept spinning at nearly the same speed as the stars near the center, as if something invisible was holding them, pulling them, keeping them from flying off into the dark. Scientists call what they found there dark matter, a name that is in some ways more of a placeholder than an answer. It tells you what the thing is not. It is not light. It does not emit or absorb radiation in any way we can detect. It simply exists in vast halos surrounding galaxies, shaping the way they move without ever announcing its presence. Researchers have since confirmed Vera Rubin's observations many times over in many different ways, and yet decades later, no one has ever directly detected a single particle of dark matter. It remains in a sense the most well-evidenced mystery in modern physics. A thing we are nearly certain is there and still cannot touch. There is something quietly humbling about that. The universe, it seems, is not obligated to be visible, but the rotation problem is only one of the ways galaxies misbehave. The more carefully astronomers map the sky, the more the universe reveals small patient anomalies. Galaxies moving in directions they have no visible reason to move. Galaxies that are enormous, but almost empty. Galaxies that simply stopped long ago as if a quiet signal passed through them, and the lights one by one began to go out. None of these anomalies are frightening. None of them suggest that the universe is broken or that our understanding is useless. They are more like gaps in a long piece of music. Measures where the expected note does not come, and in the silence something more interesting takes its place. It may be that the universe has always been more varied than our early models assumed. Scientists are still exploring this. The more instruments we build, the more clearly we can see that the cosmos is not a single, clean system obeying a small set of simple rules. It is layered, subtle, full of local exceptions and quiet departures from the expected, in a way that should not be surprising. The most interesting things in nature rarely behave exactly as predicted. Ecosystems do not follow textbooks. Weather moves in spirals no equation fully captures, and galaxies, it turns out, are no different. They are alive in the way that large, slow things are alive, moving on timescales so vast that a human lifetime is less than a flicker to them. And within that slowness, they change and shift and surprise the people who watch them. What draws astronomers back to these questions year after year is not the hope of finding a single clean answer. It is something more like the feeling you get standing outside on a clear night, looking up and realizing that what you are seeing is not the sky as it is, but the sky as it was. Light takes time to travel. Every star you see existed years ago, thousands of years ago, millions of years ago. Some of the stars visible to the naked eye no longer exist at all, and the galaxies, the furthest ones, the ones at the edge of what our telescopes can reach, they existed billions of years ago. We're not seeing them. We are remembering them, receiving a message that was sent before the Earth had finished forming. Researchers have found in those ancient signals galaxies that should not have been as large as they were, as structured as they were, as mature as they were, given how young the universe was at the time. The timeline as we understand it does not quite accommodate them, and so gently, quietly the models shift. A little more room is made, another gap in the music is acknowledged. The mind, when it encounters something it cannot fully explain, has a few options. It can feel unsettled, it can look away, or it can simply hold the question lightly the way you might hold a smooth stone in your hand without needing to know exactly where it came from. Scientists, the ones who do this kind of work well, tend to choose the third option. They carry the unanswered question with them for years sometimes. They let it sit. They return to it when something new becomes visible, and in the meantime, they keep looking. There is a particular quality to the sky on the kind of night when the air is very still and the light pollution is low, a depth to it, a sense that what you are looking at is not a ceiling, but a volume, that the darkness between the stars is not absence, but presence filled with things too faint and too distant to resolve into any image a human eye could recognize. Most of what the universe contains is like that, beyond the reach of the eye, requiring instruments, patience, mathematics, and sometimes the willingness to accept that a number that will not behave might be telling you something more important than all the numbers that do. The galaxies that puzzle us most are not the loud ones, not the ones blazing with young stars or being torn apart by collision. The ones that quietly refuse to fit the expected picture are in their own way the most interesting of all. And there are more of them than you might think scattered across the sky, carrying their small anomalies through billions of years of cosmic time, waiting with no particular urgency to be understood. The universe does not hurry, and on a night like this neither do we. Something out there is gently, quietly wrong, and the people who spend their lives looking into that wrongness describe it not with frustration, but with something closer to wonder. We will follow that wonder slowly as the night continues to deepen. There is a particular kind of patience required to study something you cannot see, not the patience of waiting for an answer to arrive. Something quieter than that, more like the patience of a person sitting beside a window at night watching the glass fog slowly from their breath, understanding that what they can observe, the faint condensation, the soft blur of the world outside, is only an outline of something much larger, something they may never see directly, and being somehow at peace with that, Astronomers who study the rotation of galaxies have learned to hold that kind of patience, because what they have found over decades of careful measurement is a universe that keeps its most important ingredients almost entirely out of sight. To understand why this is strange, it helps to begin with something more familiar, something closer. Consider the way our own solar system moves. The 8 planets and everything else orbiting the Sun follow a pattern that a 17th century mathematician named Johannes Kepler described with almost unsettling precision. Objects close to the Sun move quickly. Mercury, the innermost planet, completes its year in just 88 Earth days, rushing through its orbit at nearly 48 kilometers per second. Neptune, far out at the edge, takes nearly 165 Earth years to complete a single loop, moving at less than 6 kilometers per second. Distance and speed are linked. The further you go from the center of gravity, the slower the orbit. It is one of the most reliable relationships in all of physics, and it holds everywhere we have ever tested it, from our own solar system to the moons of distant planets to the behavior of binary stars, which is exactly why the galaxies were so surprising. When researchers began measuring how fast stars rotate around the centers of spiral galaxies, they expected the same clean pattern. Stars near the bright central bulge where most of the visible mass is concentrated should move quickly. Stars in the outer arms, far from the center and surrounded mostly by thin gas and open space, should slow down, just as Neptune slows in its long, cold loop around the Sun. What they found instead was something the equations were not prepared for. The outer stars were not slowing. They were moving at nearly the same speed as the inner ones. In some cases, the rotation curve, the graph of speed, plotted against distance from the center, ran almost perfectly flat all the way to the outer edge of the visible galaxy. A flat rotation curve should not exist. Not if the only matter in the galaxy is the matter we can see. It implies that there is something else out there, something distributed throughout the galaxy, and well beyond its visible edges, something with enough mass to keep those outer stars moving faster than they have any right to move. Scientists suggest this invisible something is dark matter. Not dark in the poetic sense, though there is poetry in the name. Dark in the technical sense, meaning it does not interact with light. It does not glow. It does not absorb. It does not scatter photons or reveal itself in any region of the electromagnetic spectrum we have yet learned to read. The only way we know it is there at all is through the motion it causes in things we can see. Evidence suggests that dark matter outweighs all the visible matter in the universe by a factor of roughly 5 to 1. For every kilogram of stars and gas and dust that we can observe, there are approximately 5 kilograms of something else, something silent distributed in vast invisible halos that extend far beyond the luminous edges of galaxies. This means that what we call a galaxy, that beautiful spiral of stars and colour in an astronomy photograph, is in some real sense only the surface of something much larger. A glowing centre inside a dark, enormous sphere of matter that we cannot photograph. The visible galaxy is something like the tip of an iceberg, though even that image undersells it. The visible part may be closer to 1/6 of the total structure. What we see when we look at a galaxy is the minority. The quiet, invisible majority surrounds it on all sides, bending the paths of stars, holding everything together, present without ever being perceived. There is something almost meditative in that idea, that the most substantial part of a thing can be invisible. That presence does not require visibility. That something can shape everything around it without ever showing itself directly. What makes dark matter stranger still is how it clusters. It does not behave the way ordinary matter does. Ordinary matter, the kind that makes up stars and planets, and people, tends to collapse under its own gravity, condensing into dense structures, clumping together, radiating heat as it does. Dark matter does not seem to do this. It remains diffuse, spread out, forming smooth halos rather than tight concentrations. Researchers have found through gravitational lensing, a technique we will return to later in this night, that dark matter halos can extend for hundreds of thousands of light years beyond the visible edges of a galaxy. They are not attached to the stars. They are not contained by the spiral arms. They simply surround, quietly enclosing the visible light the way atmosphere encloses a planet present everywhere, at once felt but not seen. Some galaxies, it has been discovered, have very little dark matter at all. A few remarkable structures called ultra-diffuse galaxies appear to rotate as if the invisible scaffolding were simply missing. This is not yet fully explained. It may be that these galaxies were somehow separated from their dark matter halos through gravitational interaction with larger neighbors. It may be that there are galaxies that formed and persisted outside the usual rules. Scientists are still exploring this carefully without rushing to a conclusion that the evidence cannot yet support. What it tells us quietly is that dark matter is not uniform. The universe does not apply it evenly. There are places where it accumulates and places where it is thin, and places where it may be almost absent. The cosmos is less like a formula and more like a terrain full of variation, full of local conditions that no single equation can fully describe. Vera Rubin, the astronomer whose work first brought this anomaly into clear focus, spent decades measuring rotation curves. She was by most accounts deeply at ease with the mystery she had helped uncover. She did not seem to experience it as a problem to be anxious about. It was more from everything recorded about her perspective like a gift. A door left open in a room you thought you knew completely. She once noted gently that every time we look carefully at the universe, we find that most of it is made of something we do not yet understand. And she seemed to find that not troubling but wonderful. It may be that the right relationship with the unknown is something like hers, not urgency, not frustration, just a steady quiet attention, a willingness to sit with the open question, to keep measuring, to let the answer come in its own time. The night sky seen from a dark place far from any city gives a faint impression of what astronomers mean when they speak about scale. The band of light across the centre, the soft blur of our own galaxy seen from the inside, represents only a small fraction of the Milky Way's total mass. The invisible halo, the dark matter surrounding us on all sides, extends far beyond what any eye can see or any photograph can capture. We are inside it in a sense, moving through it, embedded in it, shaped by its gravity at every moment. We do not feel it the way we feel the pull of the earth beneath us. It is too diffuse, too evenly distributed. But it is there in the motion of every star, in the shape of every spiral arm, in the patient flatness of every rotation curve that should by right slope gently downward and instead run straight and level into the dark. There is something deeply comfortable about that in the end. Being held by something you cannot see, moving through something too large to perceive, shaped by forces that ask nothing of you, that require no response, that simply continue steady and invisible, whether you are aware of them or not. The galaxies keep rotating, the outer stars keep their impossible speed. And somewhere in all of that invisible scaffolding, there is a kind of structure that does not need to be visible to be real. We rest inside that structure now, all of us on this small planet in this average spiral arm inside a halo of dark matter that extends far beyond anything the night sky shows us. And the sky, for all its beauty, is only the beginning of what is actually there. There are galaxies, though, where even the dark matter tells a strange story, where the shape of things is so unexpected, so at odds with what the models predict, that the scientists who study them sometimes describe the experience of looking at the data the way you might describe the feeling of reading a sentence that is grammatically correct, but somehow quietly does not make sense. those galaxies are where we are drifting next. Not every mystery announces itself with noise. Some of the most unsettling discoveries in science arrive quietly. They come the way a wrong note in familiar music comes, not loud enough to interrupt, but present enough that something in you stirs some part of the mind that was almost asleep suddenly softly awake again. The ultra-diffuse galaxies are like that. For most of the history of modern astronomy, a galaxy of a certain size was expected to contain a certain number of stars. This was not a rigid rule, but it was a reliable expectation, the way a house of a certain size is expected to contain a certain number of rooms. Scale and content were understood to be related. A galaxy as wide as the Milky Way, stretching across 100,000 light-years of space, would naturally hold hundreds of billions of stars, enough mass to generate the gravity needed to hold itself together, to spin, to persist across billions of years of cosmic time. Then, in the middle of the 20th century, and more systematically in the decades that followed, astronomers began to find galaxies that were by any conventional measure enormous in size but nearly empty of stars. They called them ultra-diffuse galaxies. And the name for once in science is almost exactly right. Imagine a structure as wide as our entire galaxy. Not slightly smaller, not comparable, the same approximate diameter. 100,000 light-years across, give or take, a span so large that light itself moving at nearly 300,000 kilometers per second would take 100,000 years to cross it. Now remove most of what is inside. Leave only a fraction of the stars, perhaps 1% of what a normal galaxy of that size would contain. Spread them out thinly across all that space the way you might scatter a handful of salt across a very large table, each grain separated from the others by enormous distances. The whole thing so faint, so sparse, so loosely assembled that it is nearly invisible against the background of the sky. That is an ultra-diffuse galaxy. Researchers have found thousands of them now in clusters and in relatively empty regions of space, some near large galaxy clusters, others more isolated. They are not rare anomalies. They appear to be a genuine category of structure formed through processes that are still not fully understood, persisting through mechanisms that challenge the standard picture of how galaxies are supposed to work. The question that presses most quietly on the mind when you encounter these structures is a simple one. How do they hold together? A galaxy with so few stars has very little visible mass. The gravitational contribution of all those scattered stars spread so thinly across such enormous distances should not be enough to prevent the whole structure from dissolving. The stars should drift apart over billions of years, dispersed by the gentle randomness of their own orbital paths, until the galaxy is no longer a galaxy at all, just a thin scattering of old stars with no shared identity. And yet many ultra-diffuse galaxies persist. They are old. Some appear to have been forming stars very early in the history of the universe, and then for reasons that vary from case to case mostly stopped. They are not falling apart. They are simply there, pale and enormous and patient, drifting through space with a kind of quiet resilience that their apparent fragility does not explain. Evidence suggests that at least some of them are held together by dark matter, the same invisible scaffolding that keeps ordinary galaxies rotating faster than their visible mass would allow. In fact, some ultra-diffuse galaxies appear to contain unusually large amounts of dark matter relative to their stellar content. The stars are sparse. The dark matter halo is intact. The galaxy is in a sense almost pure dark matter, wrapped in the faintest imaginable veil of light. But then there are others. Some ultra-diffuse galaxies appear to contain almost no dark matter at all. This is, by the standards of modern astronomy, a genuinely strange finding. Dark matter is supposed to be everywhere. It is supposed to make up most of the mass of every galaxy, the unseen foundation on which everything else is built. Finding a galaxy-sized structure with little or no dark matter is something like finding a building with no foundation, standing somehow inexplicably simply because it has not yet been given a reason to fall. One of the most studied of these is a galaxy known in astronomical catalogues by a designation that translates in plain language to nothing particularly poetic. But what scientists found when they analysed its motion was remarkable. The stars in this galaxy move at speeds consistent with what you would expect from their visible mass alone. No dark matter appears to be needed to explain their motion. No invisible scaffolding, just the stars themselves holding each other with nothing more than what they visibly are. What we understand so far suggests a few possible explanations. One is that this galaxy was stripped of its dark matter by a close encounter with a much larger neighbour, a gravitational interaction that pulled the invisible halo away while leaving the stars behind. Another possibility is that the dark matter was never there in the same proportion that this galaxy formed under unusual conditions that resulted in a different balance from the start. A third possibility, quieter and more philosophically interesting, is that our models of how galaxies form and retain dark matter are still incomplete, that there is something in the behaviour of matter at these scales that we have not yet fully accounted for. Scientists are still exploring all of these possibilities simultaneously without insisting on a premature resolution. There is something in the willingness to hold multiple explanations open at once that feels almost like a kind of intellectual softness, not weakness, not indecision, but the specific grace of a mind that has learned not to close a door before it knows what is on the other side. The ultra-diffuse galaxies do not demand resolution. They simply exist scattered through the universe in their quiet thousands, each one a variation on the theme of vastness and sparseness, each one a small reminder that the universe contains more categories of thing than any single model can anticipate. It may be that the most honest position when faced with something that does not fit the expected picture is exactly this: to note it carefully, to measure it precisely, to resist the urge to force it into a shape it does not naturally hold, and to keep the question alive gently for as long as it takes. There is a particular kind of light that reaches us from these galaxies, not the sharp, concentrated light of a dense spiral arm or a blazing core. Something softer, diffuse and low in surface brightness, the kind of glow that is easy to miss if you're looking for something brighter, the kind that only becomes visible when you specifically calibrate your instruments to find it. Astronomers call this low surface brightness. It is a technical term, but the image it creates is strangely gentle, a galaxy so faint it seems almost reluctant to be seen, spread across such a large area of sky that no single patch of it is bright enough to catch the eye, the whole only visible when you step back far enough to see all of it at once. It may be that some of the most interesting things in the universe share this quality. Present everywhere at once, visible only from a certain distance, undetectable to instruments calibrated for brightness. Researchers have begun building new tools specifically to find more of them. Surveys designed not to find the brightest objects but the faintest. Not the most obvious but the most easily overlooked. And with each new generation of instruments, more of these pale, enormous structures emerge from what was previously assumed to be empty sky. The universe is not emptier than we thought. It is fuller in ways that quieter methods of looking are only beginning to reveal. What stays with you after spending time with the idea of ultra-diffuse galaxies is not the strangeness. It is the scale of the ordinary. The fact that a galaxy by definition is a structure large enough to hold billions of stars, and that even these nearly empty ones, these sparse and fragile-seeming arrangements of old stars and thin gas, are still larger than most people could hold in their imagination for more than a moment. 100,000 light-years of almost nothing, and within that almost nothing stars that are still burning, still moving, still held together by whatever combination of gravity and history brought them to where they are. There is a kind of company in that, in the knowledge that even the most diffuse and scattered things in the universe are still in their own way structured, still part of something, still persisting in their quiet and unremarkable way across billions of years. And what makes these pale galaxies stranger still is what researchers quietly noticed when they looked at their neighbours. Because galaxies, it turns out, do not drift through the universe in isolation. They are pulled, shaped by what surrounds them, and some of them are moving in directions that have taken decades of careful observation to even begin to understand. There is a current running through the universe, not a metaphor, not a poetic image borrowed from rivers or tides, an actual current, a vast and slow movement of galaxies across hundreds of millions of light-years of space, flowing in a direction that took decades to even confirm was real. A drift so large and so gradual that the instruments needed to detect it had to be extraordinarily sensitive, calibrated to notice changes of velocity measured across the full span of the observable sky. We are part of it. The Milky Way is moving within it right now, carried along by something we cannot see from the inside the way a leaf on the surface of a river cannot feel the full shape of the current that holds it. To understand this, it helps to start with what the universe is supposed to be doing. Since the early 20th century, scientists have understood that the universe is expanding. Every galaxy on average is moving away from every other galaxy, not because they are flying apart through pre-existing space, but because the space between them is stretching. The further apart two galaxies are, the faster they appear to be separating simply because there is more space between them to expand. This is called the Hubble flow after the astronomer Edwin Hubble, whose observations in the early decades of the 20th century helped establish it. And for galaxies far enough apart, it dominates everything. Distance drives recession. The universe grows and galaxies ride its expansion, the way objects float on the surface of an inflating balloon. But locally within clusters and superclusters of galaxies, gravity is strong enough to override that expansion. Nearby galaxies pull on each other, tug on each other, sometimes merge. And this local gravity creates motions that do not follow the simple Hubble flow movements, called peculiar velocities, a technical term that does not quite capture how genuinely strange some of them are. In the 1980s, a group of astronomers known informally as the Seven Samurai, a name they gave themselves with the kind of quiet wit that sometimes surfaces in long-term collaborative work, began a systematic study of the peculiar velocities of elliptical galaxies. They were trying to map how galaxies in our cosmic neighbourhood were moving relative to what the Hubble flow predicted. What they found was that a large region of space containing our own galaxy, the Andromeda Galaxy, the Virgo cluster, and thousands of other galaxies spanning several 100 million light-years, was all moving in roughly the same direction. Not randomly, not in a scatter of individual trajectories, together streaming as if drawn by something. They called the source of that pull the Great Attractor. It lies in the direction of the constellation Centaurus, a region of sky that from the northern hemisphere is largely below the horizon, and obscured by the disk of our own galaxy, a band of stars and dust that blocks the view, precisely where the most interesting thing in our cosmic neighbourhood is apparently located. It is one of the more charming inconveniences in the history of astronomy that the thing pulling us has spent decades hiding behind us. Researchers have found through painstaking work using radio telescopes and infrared surveys that can penetrate the obscuring dust of our galaxy's disk that the Great Attractor region contains an enormous concentration of mass. Several large galaxy clusters, hundreds of thousands of individual galaxies embedded within a larger structure now called the Laniakea supercluster, a name drawn from the Hawaiian for immeasurable heaven. Laniakea as a structure spans roughly 500 million light-years. It contains the mass of approximately 100 million billion suns, and within it our galaxy and everything near us sits near one edge, slowly drifting toward the denser central region, the way water on a tilted surface moves not quickly, not dramatically, but persistently following the landscape of gravity. It seems that we have always been in motion in this direction for as long as the Milky Way has existed. Not fleeing, not rushing, just drifting gently and continuously along a gradient so smooth and so large that nothing within it would notice the movement in any human lifetime. And yet even within Laniakea there are galaxies that appear to be moving against the general flow. Some galaxies in the local group, the small cluster of roughly 80 galaxies that includes the Milky Way, are moving toward us rather than away. The Andromeda Galaxy, the large spiral nearest to us, is approaching at roughly 110 kilometers per second. In roughly 4.5 billion years, the two galaxies will interact gravitationally, and the resulting structure will be something neither currently resembles. This is not alarming. It is, by the unhurried standards of cosmic time, simply what happens when gravity is strong enough and distances are small enough. Galaxies in clusters do not follow the Hubble expansion, because they are bound to each other, held in mutual orbits the way the Moon is held to the Earth, unable to drift away, because the pull between them exceeds the expansion of the space that separates them. But there are cases further out where the motion is harder to explain. Galaxies in the outskirts of clusters, galaxies that should by the models be on their way outward, with the expansion, instead seem to be falling back in or moving sideways or oscillating in patterns that suggest the gravitational landscape is more complex than a simple sphere of matter would produce. What we understand so far suggests the universe is lumpy in ways that influence motion, across scales far larger than any single galaxy or cluster. The filaments of the cosmic web, the vast sheets and walls of galaxies connected across hundreds of millions of light-years, create gravitational gradients that persist across that entire span, shaping the motion of everything embedded within them. There is something quietly humbling about learning that even on the larger scales nothing is perfectly still. The universe does not have a flaw. It does not have a fixed reference point from which all motion can be measured. Every observer is already in motion. Every frame of reference is itself moving within a larger one. Physicists have understood this formally since Albert Einstein's work in the early 20th century, but the galaxy surveys of recent decades have made it viscerally real in a way that equations alone cannot quite convey. When you watch the visualization of a Laniakea, that enormous map of supercluster structure, with its filaments and voids and the small bright dot marking our position near the edge, something shifts in the mind. Not toward anxiety, toward a kind of quiet recalibration. The sense of being rooted somewhere, of having a fixed position, is comfortable. It is something the mind returns to naturally, the way a body returns to rest after exertion. But the universe, it may be, does not share that preference. It is in motion at every scale, from the electrons in an atom to the superclusters of galaxies, and what we call stillness is always relative, always local, always a temporary agreement between things that are in truth always moving. There is also in the story of the Great Attractor a reminder of how much of the universe remains invisible to us for entirely mundane reasons. Not because the physics is exotic, not because the instruments are insufficient, simply because our galaxy's disk, that beautiful band of stars and nebulae that fills a clear night sky with soft light, happens to lie between us and a significant portion of the observable universe. Astronomers call this the zone of avoidance, the region of sky where the density of our own galaxy's stars and dust makes it effectively impossible to see what lies beyond. The Great Attractor hid there for years. Other structures likely remain hidden there still. Evidence suggests that there are additional concentrations of mass in that obscured region, pulling on our local supercluster in ways that are still being mapped and modelled. It is a strange and specific kind of not knowing. We can describe the gravitational effect with precision. We can measure the velocity it produces across hundreds of millions of light-years of galaxies. We simply cannot see it directly because our own home is in the way. There is something almost endearing in that. All that mass pulling everything in this corner of the universe gently in one direction. And for a long time we could not even confirm it was there, because the glow of our own sky was too bright, our own galaxy, too opaque, our own position, too embedded in the very thing we were trying to observe. The universe does not make it easy to see from the inside, but that has never stopped the looking, and as the looking continues, as the maps grow more detailed, and the surveys reach further into the obscured and the unfamiliar, new shapes emerge, new currents, new sources of pull. Some of those sources are not moving matter at all. They are absences, places where matter stopped long ago, and what remained was a different kind of shape entirely. When two galaxies collide, no one gets hurt. That is not a metaphor or a reassurance or a way of softening something frightening. It is simply what happens. Two structures each containing hundreds of billions of stars moving toward each other across millions of light-years, eventually occupying the same region of space, and yet the stars themselves almost never touch. The distances between them are too vast. The probability of any two stars actually colliding in the ordinary physical sense is extraordinarily small. What happens instead is something stranger and in some ways more interesting. The galaxies pass through each other like two clouds of smoke moving in opposite directions, interpenetrating, disturbing, reshaping, and leaving behind something that is neither of the things that came before. To understand why the stars do not collide, it helps to hold the scale of a galaxy in mind for a moment. The nearest star to our Sun is a small red dwarf called Proxima Centauri. It sits approximately 4 light-years away. 4 years of light travel time, a distance so large it is difficult to feel with any real intuition. If the Sun were the size of a grain of sand. Proxima Centauri would be another grain of sand roughly 5 kilometers away. Almost everything between them is nothing. Vacuum. The near-perfect emptiness of interstellar space. Now multiply that emptiness across 100,000 light-years and fill it with a few 100 billion grains of sand, each one separated from its neighbours by similar distances. That is a galaxy. Mostly empty, vast and mostly nothing, with stars scattered through it at intervals that make collision even during a full galactic merger vanishingly unlikely. The stars drift through each other's presence without touching the way two crowds of people might pass through each other in a very large open space, each individual moving on their own trajectory, rarely intersecting with anyone from the other group, the whole event taking longer than any human lifetime to complete. But if the stars do not collide, something else does. The gas does. Galaxies are not only stars. Threaded between the stars in enormous clouds and filaments and diffuse halos is gas, primarily hydrogen and helium, the raw material from which stars form. This gas is compressible. It responds to pressure, to shock waves, to the turbulence created when two vast gaseous envelopes meet at speed. When galaxies merge, their gas clouds collide violently in the physical sense that stars do not. Shock waves propagate through the interstellar medium. Gas is compressed, temperatures rise, and in those compressed heated regions something remarkable often happens. The conditions for star formation are suddenly abundantly met. New stars ignite across the merging system in what astronomers call a starburst, a period of dramatically accelerated stellar birth triggered by the collision itself. Researchers have found that merging galaxy pairs often show starburst activity orders of magnitude more intense than anything in a quiet, undisturbed galaxy. Thousands of new stars forming every year in systems that before the merger might have formed only a handful. The collision that disrupts also creates. The disturbance that reshapes also generates. There is something in that worth sitting with. The same event that pulls a galaxy out of its long-established shape, that distorts its spiral arms and scatters its outer stars into long tidal streams across millions of light years, is also the event that fills it with the brightest, youngest stars it will ever contain. The timescales involved are difficult to hold in the mind, and in a way that difficulty is part of what makes them restful to contemplate. A typical galactic merger takes somewhere between hundreds of millions and a few billion years to complete. The initial approach, as two galaxies fall toward each other under mutual gravitational attraction, can last for billions of years before they even make first contact. The first pass when the two systems begin to interpenetrate might take a few 100 million years. Then, having passed through each other, they slow turn and fall back together for a second pass, and a third. Each pass closer, each encounter more disruptive, until eventually the two systems can no longer separate, and their stars, gas and dark matter halos, begin the slow process of mixing into a single new structure. From the point of view of any star within the merging system, almost nothing happens on the scale of a human lifetime. The sky might shift slowly over millions of years. New stars might appear in regions that were previously quiet. The shape of the galaxy, as seen from within, might gradually distort over timescales too long for any individual to perceive. It is the gentlest kind of violence, imaginable violence, so slow it is indistinguishable from peace. What remains after a merger is complete is often an elliptical galaxy. Spiral galaxies have structure, those beautiful rotating arms, the organized sweep of stars following ordered orbits. But when two spirals collide and merge, that organization is disrupted. The orbital memories of both systems interfere with each other, the way two sets of ripples on a pond create patterns that belong to neither source individually. The result after enough time is a smoother, rounder structure. The stars distributed more randomly in their orbits, the elegant spiral pattern dissolved into something older looking and more settled. Most of the largest galaxies in the universe are ellipticals, and it seems that many of them grew to their current size through mergers accumulating mass over billions of years by absorbing smaller neighbors, each absorption adding stars and gas and dark matter to the growing whole. In this sense, the history of a large galaxy is written in its shape. A smooth, featureless elliptical carries within it the accumulated record of every galaxy it has ever absorbed, every merger that added its stars to the mix, every collision that contributed to the final form. It is a palimpsest of interactions, each layer of history invisible, now dissolved into the overall structure, but present in the distribution of stars, the kinematics of their orbits, the chemical composition of the gas that remains. The Milky Way itself is not innocent of this history. Evidence suggests that our galaxy has merged with numerous smaller galaxies over its lifetime, absorbing dwarf galaxies and satellite structures in events that left their traces in the distribution and chemical composition of certain populations of stars. There are streams of stars in the halo of our galaxy, long filaments of stars all moving in similar directions that appear to be the remnants of dwarf galaxies disrupted by the Milky Way's gravity over billions of years, their stars scattered into the halo like the memory of something that no longer exists as a coherent object. One of the most significant of these past mergers, now called Gaia Sausage Enceladus, by researchers appears to have occurred roughly 8 to 11 billion years ago, when the Milky Way absorbed a galaxy roughly the size of the Large Magellanic Cloud. The stars from that ancient merger are still identifiable today, recognizable by their orbital characteristics and chemical signatures, moving through the galaxy on orbits that reflect their origins in a structure that no longer exists. What we understand so far suggests that the Milky Way we inhabit is in part built from at least one galaxy that is no longer there, that somewhere in the population of stars surrounding us, some of them formed in a different galaxy entirely, one that completed its existence by becoming part of ours. The Andromeda Galaxy, which researchers have confirmed is approaching the Milky Way at roughly 110 kilometers per second, will likely begin a gravitational interaction with our galaxy in roughly 4 to 5 billion years. The eventual merger, if it proceeds as models suggest, will take several billion years more to complete. The resulting structure, sometimes called Milkomeda or Milkdromeda in astronomical shorthand, will likely be an elliptical galaxy, larger than either of its predecessors, quieter in terms of star formation as the gas supply is gradually consumed. The spiral arms of both galaxies, those elegant structures that can be seen in photographs taken across hundreds of millions of light years, will dissolve into the more diffuse rounded shape that large merged galaxies tend to settle into. No star in either galaxy is likely to collide with another. The night sky, as seen from any planet that survived the process, would look different, filled with the light of both galaxies, mingling brighter than any sky we know, but not dangerous. Not the end of anything in the physical sense. Just a very long, very slow reorganization of the same stars and gas into a new configuration, a new shape, carrying within it the memory of two spirals that once existed separately, now dissolved into something neither was before. It may be that this is one of the quieter truths the universe offers through the long story of galaxy mergers, that things which appear stable and permanent are on longer timescales fluid. That structure is not the final state of matter, but a temporary agreement subject to revision by gravity and time, and that what emerges from disruption is not necessarily lesser than what came before. The elliptical galaxies that populate the centers of large clusters, those enormous, smooth, ancient structures, are in some sense the most experienced objects in the visible universe. They have absorbed the most. They have been shaped by the most interactions. They carry the longest history. And they are also in their way very quiet. There is a certain kind of galaxy, though, where quietness is not the result of age or merger or disruption. It is something more deliberate, something that happened from within a switching off so complete and so final that the galaxy has not recovered in billions of years. Those are the ones worth looking at next gently in the slow hours of this night. There are galaxies in the universe that glow blue, not metaphorically, not in the way we sometimes use colour to describe a mood or a quality. Physically measurably blue, their light shifted toward the shorter wavelengths of the visible spectrum, because they're filled with young, massive, extraordinarily hot stars that burn intensely and briefly, pouring out enormous quantities of ultraviolet and blue-white light before exhausting themselves in a few million years. A galaxy full of young stars is a galaxy still actively forming them, still pulling gas together, still collapsing clouds of hydrogen into the dense heated cores where nuclear fusion ignites. These galaxies are in a sense alive with process, noisy with creation if you could hear it, bright with the particular brightness of things that are young and burning fast. And then there are the others. Astronomers call them red and dead. It is a blunt phrase for what is in its way a quietly profound condition. These galaxies, mostly large ellipticals, glow in the longer wavelengths, the oranges and reds, not because anything dramatic happened to them, but because the stars that remain within them are old. The blue-white giants burned through their fuel long ago and are gone. What persists are the cooler, slower stars, the ones that burn dimly and patiently, for billions of years, the ones that do not rush. The galaxy itself has not died in any catastrophic sense. Its stars are still burning, Its gravity still holds everything in place. But new stars are no longer forming. The raw material for star birth, the cold gas clouds that collapse under their own gravity and ignite into suns, has been depleted or heated or expelled. The galaxy has entered a state that researchers sometimes describe as quenched, a term that carries in its physicality something of the right feeling. Something that was burning has been put out. What makes this strange, and what has occupied astronomers for several decades now, is the question of what quenches a galaxy. Running out of gas is one answer, but it is not the complete one. Galaxies in the process of being quenched sometimes still have gas. The gas is simply not forming stars. It has been heated to temperatures too high for the gravitational collapse that star formation requires. Something has injected energy into the interstellar medium, keeping it warm, keeping it diffuse, preventing it from cooling into the dense clumps from which stars are born. Evidence suggests that the most likely culprit in many cases is the galaxy's own central black hole. Most large galaxy scientists now understand harbour a supermassive black hole at their centre. These objects range from millions to tens of billions of times the mass of the Sun compressed into a region smaller than our solar system. A concentration of mass so extreme that the surrounding space is fundamentally altered by its presence. When a supermassive black hole is actively drawing in gas from the surrounding galaxy, it releases enormous quantities of energy, not quietly. The infalling matter forms a rotating disk heated by friction to temperatures of millions of degrees, and as some of that matter spirals in powerful jets of plasma and radiation, are launched outward along the black hole's rotational axis, perpendicular to the disk at close to the speed of light. These jets can extend for hundreds of thousands of light years far beyond the visible edges of the galaxy itself, and they carry with them enough energy to heat the gas of the entire galaxy, and even the intergalactic medium surrounding it, raising temperatures throughout the system to levels that prevent star formation for millions or even billions of years. What we understand so far suggests that this feedback process, the black hole feeding on the galaxy's gas, and in doing so heating that same gas to prevent further star formation, is one of the primary mechanisms by which large galaxies are quenched. The black hole silences the very system that gave it the material to grow. It is a strange and circular kind of causation. The galaxy needs gas to form stars. The stars over their lifetimes enrich the gas with heavier elements and return it to the interstellar medium. Some of that gas falls toward the center, feeding the black hole. The black hole, in consuming it, releases energy that heats the remaining gas throughout the galaxy, and the heated gas can no longer collapse. Star formation slows. Eventually it stops. The galaxy does not choose this. There is no intent in any of it. It is simply what happens when certain conditions are met, when a black hole is massive enough, and its energy output sustained enough, and the gas supply warm enough for long enough. The system finds a new equilibrium, quieter, older, no longer making new things but persisting in the state it has settled into. Researchers have found that the mass of a galaxy's central black hole correlates remarkably well with the properties of the galaxy's central bulge, the density of stars, their average velocities, the mass of the whole structure. This correlation holds across many orders of magnitude, from relatively modest black holes in smaller galaxies to the most enormous ones at the centers of the largest ellipticals. It seems that the black hole and the galaxy grow together, regulate each other, shape each other across billions of years of shared history. They are not separate things that happen to occupy the same space. They are in some meaningful sense a single system. There is something in that relationship worth pausing with. The largest, most energetic object in a galaxy, the thing capable of launching jets that travel for hundreds of thousands of light years and heat gas across a volume of space 1 billion times larger than the solar system, is also the thing that ultimately brings the galaxy to rest. The most powerful engine is also the off switch. The force that could, in principle, drive enormous activity is the same force that eventually quiets everything down. It may be that this is not a paradox but a pattern. That in complex systems, the things with the most energy are also eventually the things that bring the system toward equilibrium. That rest in the long view is what energy tends toward. The red and dead galaxies carry their history in their light. The reddish glow of an old stellar population is not sadness. It is not decline in any meaningful evaluative sense. It is simply the signature of age, the particular color that a collection of stars takes on when the young and bright ones have already lived and gone, and what remains are the steady, patient, long-burning ones. Some of the oldest stars in the observable universe are found in quenched elliptical galaxies, stars that formed in the first few billion years of cosmic history, when the universe was denser and hotter, and the raw materials for star formation were everywhere abundant. Those stars are still burning slowly and quietly in galaxies that have not made a new star in billions of years. They will continue burning for longer than the current age of the universe has lasted. The red dwarf stars, especially the smallest and coolest and most common, have lifetimes estimated in the trillions of years. Long after the sun has expanded and cooled, and the solar system has changed beyond recognition, these old quiet stars in old quiet galaxies will still be burning, still warming whatever orbits them, still present in a universe that has grown much darker and much more diffuse around them. Scientists are still exploring the full picture of galaxy quenching. There are mechanisms beyond black hole feedback environmental effects that strip gas from galaxies falling into clusters, internal processes related to the exhaustion of cold gas reservoirs, gravitational interactions that heat the interstellar medium. For many quenched galaxies, the answer is probably some combination of several processes acting over billions of years, no single cause decisive on its own. What all the mechanisms share, though, is the theme of energy and equilibrium. The galaxy receives energy from stellar winds, from supernova explosions, from the jets of its central black hole, and over time that energy disperses through the system until everything has settled into a state that no longer supports the conditions for new creation. It is not an ending. It is a settling. The way a very long day, eventually without drama, becomes night. There is a quieter layer to this, though one that most people never consider. Because the black holes at the centers of these galaxies, even the quiet ones, even the ones in galaxies that stopped making stars 1 billion years ago, are still there, still present, still capable given the right conditions of waking. And somewhere in the universe right now there are black holes doing exactly that, not at the centers of old and quiet galaxies, but grown to proportions that change the entire neighborhood around them. There is a relationship in astronomy that no one expected to find. It was not predicted by theory before it was observed. It was not the result of a deliberate search for a connection. It emerged the way some of the most interesting things in science emerge from data collected for entirely different purposes, patterns noticed quietly at the edges of what was already known, a correspondence so consistent and so precise that ignoring it became impossible. The relationship is this: the mass of the supermassive black hole at the center of a galaxy correlates with remarkable tightness with the velocity of stars in the galaxy's central bulge. Not the total mass of the galaxy, not the number of stars, not the size of the disk or the shape of the spiral arms. Specifically the velocity dispersion, the average spread of speeds among stars in the dense central region, a measurement that serves as a proxy for the depth of the gravitational well at the galaxy's heart. Astronomers call it the m-sigma relation, where m refers to the mass of the black hole and sigma to the stellar velocity dispersion. And what it says in plain language is that somehow, across an enormous range of galaxy types and sizes, The black hole always seems to know how big its galaxy is. This should not be possible, not obviously. A supermassive black hole, even one containing billions of times the mass of the Sun, occupies a region roughly the size of our solar system at its innermost extent. The event horizon, the boundary beyond which nothing returns, is measured in light hours to light days depending on the black hole's mass. The galaxy surrounding it spans hundreds of thousands of light years. The black hole is in proportional terms unimaginably small relative to the galaxy it inhabits. If the galaxy were the size of the continental United States, the black hole would be smaller than a single marble somewhere near the center. And yet the mass of that marble correlates precisely with the properties of the entire continent around it. How does something so small know so much about something so large? Researchers have spent several decades working through the possible answers, and what has emerged is a picture of deep mutual influence operating across cosmic time. The current understanding still being refined is that galaxies and their central black holes do not simply coexist. They grow together, they regulate each other. They are coupled systems linked across vast distances by the energy that black holes release when they feed, and the effect that energy has on the gas supply of the entire galaxy. When a black hole is actively accreting, pulling in gas from its surroundings, it can release energy equivalent to a significant fraction of the mass energy of everything it consumes. Some of this energy goes into radiation, some into those powerful relativistic jets described in the previous hour of this night, and some couples directly to the gas in the surrounding galaxy, heating it, pushing it outward, regulating how much material remains available to fall further inward. This creates a self-regulating loop. The black hole feeds, releases energy, heats. The gas reduces the supply of infalling material, and so feeds more slowly. When the gas cools again, it falls inward, and the black hole feeds more actively once more. The system oscillates around an equilibrium that is determined ultimately by the depth of the gravitational well, which is what stellar velocity dispersion measures. It seems that this feedback mechanism operating over billions of years naturally produces the tight correlation between black hole mass and galaxy bulge properties that observers have found. The black hole grows until it is massive enough that its feedback energy averaged over time is sufficient to regulate the gas supply of its entire host galaxy. At that point, further growth slows dramatically. The system has found its natural scale. There are galaxies, though, where this balance appears to have been disrupted. Some of the most striking cases involve what astronomers call overmassive black holes, central black holes whose mass is dramatically larger than the M-sigma relation predicts for their host galaxy. These are not small discrepancies. In some cases, the black hole appears to be 10 or even 100 times more massive than the surrounding galaxy would suggest. One of the most studied examples sits at the center of a galaxy designated in astronomical catalogues by a name that's purely technical, but the object itself is anything but unremarkable. Its central black hole contains mass equivalent to roughly 17 billion suns, making it one of the most massive black holes ever measured in a galaxy of its size. The host galaxy is large by ordinary standards, but not extraordinarily so. The black hole is simply by any conventional expectation far too big for what surrounds it. Evidence suggests several possible explanations. One is that the galaxy was once much larger, and the black hole grew to a size appropriate for that earlier, more massive host, but the galaxy subsequently lost much of its stellar mass through gravitational stripping by larger neighbors in a dense cluster environment. The black hole remains its mass unchanged, now residing in a galaxy that has been reduced around it. Another possibility is that the black hole grew unusually fast in the early universe during an epoch when gas was more abundant and the conditions for rapid accretion were more commonly met. In the densest early environments, some black holes may have experienced growth episodes so intense and so sustained that they overshot the equilibrium mass that the feedback mechanism would normally enforce, scientists are still exploring both possibilities and others without having settled definitively on a single cause. It may be that overmassive black holes are not a single phenomenon with a single explanation, but a category containing several distinct formation histories that happen to produce a similar observable result. What makes these objects compelling beyond the numbers is what they imply about the galaxy's past. A black hole is a record, not in any simple readable way, but in the sense that its mass at any given moment is the accumulated result of every feeding episode in its entire history, every period of rapid accretion, every merger with another black hole, every sustained episode of growth that preceded the current quiet. The mass is the memory. An overmassive black hole carries within it the history of a galaxy that at some point in its past was either much larger, or much more gas-rich, or much more actively feeding than anything in its current appearance would suggest. Looking at such a galaxy today, quiet and unremarkable in its outward form, and knowing the mass of what sits at its centre, is a little like finding a very old scar on something that otherwise looks young. The surface tells one story, the deeper record tells another. There is also the question of what happens when two galaxies merge and both carry supermassive black holes. When two galaxies begin the long process of merger described earlier in this night, their central black holes do not immediately combine. The two black holes, each orbiting the new merged system's center of mass, gradually lose energy through gravitational interactions with surrounding stars spiraling inward over hundreds of millions to billions of years, until they are close enough that gravitational wave emission becomes the dominant energy loss mechanism. At that point, the two black holes begin to spiral together very rapidly, by astronomical standards losing energy to ripples in space-time itself, and eventually merging in an event that releases more energy and gravitational waves than all the stars in the observable universe release in light concentrated into a final fraction of a second. Researchers have detected the gravitational waves from stellar mass black hole mergers events, involving black holes of a few tens of solar masses, through the extraordinary sensitivity of gravitational wave detectors built in the United States and Europe. The mergers of supermassive black holes billions of times more massive would produce gravitational waves at far lower frequencies in the range, detectable by arrays of precisely timed pulsars spread across the galaxy, rather than by Earth-bound instruments. What we understand so far suggests that these pulsar timing arrays may already be detecting the background hum of countless supermassive black hole mergers happening throughout the universe, a faint low-frequency gravitational wave background, woven into the fabric of space-time itself, the accumulated whisper of every black hole merger that has ever occurred across cosmic history. The mind quietly registers something sitting with this idea, that the universe carries within its geometry the record of its own history. That space itself, the medium through which everything moves, is not a neutral backdrop but a living record subtly distorted by every massive event that has ever occurred, every collision, every merger, every moment of extreme gravity reshaping the fabric that holds everything else. The gravitational waves from a supermassive black hole merger 1 billion light-years away pass through you as you lie here. They stretch and compress the space you occupy by an amount so small it is incomprehensible, smaller by many orders of magnitude than the diameter of a proton. But they are real. They are present. They are the universe communicating across distances that light itself takes billions of years to cross. There is something deeply settling about that image, not the scale which is too large to feel, but the gentleness of it, a wave passing through everything, disturbing nothing, perceptibly carrying information, about events so distant and so old that the galaxies involved have long since merged and quieted and grown into something new. The black holes at the centres of galaxies are in this sense not endings. They are not simply the place where things fall in and are lost. They are the most sensitive recorders in the universe, encoding in their mass the entire history of the material and the interactions that shaped them. They are heavy with time, and the galaxies around them shaped by that mass, regulated by that feedback, quenched or sustained or disrupted by the energy released over billions of years of mutual influence, carry the same history in a different form. In the velocities of their stars, in the temperature of their gas, in the shape of their light, everything speaks if you know what to listen for. And sometimes the universe communicates not through mass or velocity or temperature, but through the simple behavior of light itself, bent and redirected by gravity into shapes that no one anticipated until the mathematics predicted them, and the observations confirm them quietly exactly as described. That is where the night takes us next. Light does not always travel in a straight line. This is one of those statements that sounds wrong the first time you hear it, then gradually as you sit with it, begins to feel like something you almost already knew. We are accustomed to thinking of a light as the straightest thing in nature, the standard by which straightness is defined. A beam of sunlight cutting through a dusty room, a laser dot moving across a wall, straight, precise, unwavering. But light travels through space, and space is not flat. Space curves in the presence of mass. Any mass from the smallest stone to the largest galaxy cluster warps the geometry of the space around it, creating subtle gradients in the fabric through which light moves. And light following the natural geometry of that warped space follows curves. Near small objects, the effect is immeasurably tiny. Near a galaxy, it becomes detectable. Near a galaxy cluster, it becomes dramatic. And in the right alignment between a distant source of light and an observer with a massive object positioned precisely between them, it produces something that looks in an astronomical photograph almost too beautiful to be real. Albert Einstein predicted this effect mathematically in the early 20th century as a consequence of his general theory of relativity. The theory described gravity not as a force acting across empty space, the way Isaac Newton had framed it, but as a curvature in the geometry of space-time itself created by the presence of mass and energy. And if space-time curves around mass, then anything moving through space-time, including light, must follow those curves. The first observational confirmation came during a solar eclipse in the year 1919, when astronomers measured the apparent positions of stars near the edge of the sun's disk and found that they were shifted slightly from their expected positions. The sun's gravity was bending the path of the starlight passing close to it, displacing the apparent position of the stars by almost exactly the amount Einstein's equations predicted. It was a quiet moment in the history of science, a prediction confirmed, a theory validated, and the beginning of an understanding that would decades later turn out to give astronomers one of the most powerful tools they possess for studying the universe. Gravitational lensing, as it came to be called, occurs whenever a massive object lies between a distant light source and an observer. The mass deflects the light, bending it around its edges, and the observer receives light that has been redirected from its original path. The simplest case produces a brightening. Light that would have missed the observer entirely is bent toward them, making the background source appear brighter than it would without the lensing object in the way. This microlensing effect is used today to search for compact dark objects in the halo of our galaxy, detecting brief brightenings of background stars as unseen objects pass in front of them. When the alignment is more precise and the lensing mass more concentrated, the deflected light can arrive at the observer from multiple directions, simultaneously creating multiple images of the same background source. A single distant galaxy, seen through a massive foreground galaxy or cluster, can appear as 2, 4, or even more separate images arranged around the lensing object, each one showing the same background galaxy at a slightly different angle and a slightly different moment in time, because the different light paths have different lengths and so take slightly different amounts of time to traverse. And when the alignment is almost perfect, something else happens entirely. If the background source, the lensing mass, and the observer are arranged along almost exactly the same line of sight, the light from the background source is bent not into a small number of discrete images, but into a continuous ring spread symmetrically around the lensing object, a circle of light surrounding a galaxy or cluster like a luminous halo. Astronomers call these Einstein rings. They are among the most visually arresting objects in the observational record. A ring of light, sometimes narrow and precise, sometimes broad and softly glowing, centered on a galaxy that has nothing to do with the light forming the ring. The ring is the image of something else entirely, something far more distant, its light wrapped all the way around an intervening mass and delivered to the observer from every direction simultaneously. The galaxy in the center does not know it is making a ring. It has no awareness of the light bending around it. It simply exists with its mass, and the universe curves around that mass, and the light from a distant galaxy travels those curves and arrives at a telescope billions of light years away in the shape of a perfect circle. Researchers have found hundreds of Einstein rings and partial rings in surveys of galaxy clusters and in systematic searches of wide-field astronomical images. Each one is a coincidence of geometry, the chance alignment of 3 things across billions of light-years of space. Each one reveals something about the mass of the lensing object, about the distance and properties of the background source, and about the distribution of matter, including the dark matter we cannot see directly in the foreground system. This is one of the most elegant aspects of gravitational lensing as a scientific tool. It measures mass directly regardless of whether that mass is luminous. A dark matter halo surrounding a galaxy bends light just as effectively as the visible stars. The lensing effect does not distinguish between matter we can see and matter we cannot. It responds to all of it, equally encoding the total mass of the lensing system in the geometry of the images it produces. Studies indicate that gravitational lensing analyses of galaxy clusters have confirmed independently of galaxy rotation curves and other methods that the visible matter in clusters accounts for only a small fraction of the total mass. The dark matter halos invisible to every other kind of observation make their presence known through the curvature they impart to the light of background galaxies, stretching and distorting those background images into arcs and rings that map the dark matter distribution as precisely as any visible structure. Some galaxy clusters produce dozens of gravitationally lensed arcs simultaneously, each one the distorted image of a different background galaxy, all of them bent by the same foreground mass. Astronomers use these multiple arcs together to reconstruct detailed maps of how mass is distributed throughout the cluster, including its dark matter component in a process sometimes called cluster mass tomography. The result is a map of something invisible drawn entirely in light. There is a quality to gravitational lensing that feels on reflection like something about the nature of information in the universe. Nothing is truly hidden. Mass leaves traces in the geometry of space. Those geometric traces are written into the paths of every photon that passes nearby. And a patient observer positioned at the right distance and equipped with the right instruments can read those traces and reconstruct the presence and distribution of matter that no light has ever directly touched. The universe communicates through its geometry. It encodes mass in curvature and curvature in the trajectories of light, and the trajectories of light in the patterns of what we see. There is a chain of physical consequence running from the most invisible mass in the universe to the image on a detector at the end of a telescope, and the chain is unbroken and exact. What we understand so far suggests that lensing will become even more powerful as the next generation of telescopes comes into operation, instruments capable of surveying the entire sky with sufficient depth and resolution to detect lensing signals from much fainter and more distant sources than are currently accessible. The maps of dark matter that these surveys will produce will cover not just individual clusters, but the large-scale structure of the universe, tracing the cosmic web itself through the subtle distortions it imprints on the shapes of billions of background galaxies. There is also a subtler form of lensing worth dwelling on for a moment. Weak gravitational lensing produces not distinct arcs or rings, but tiny statistical distortions in the shapes of background galaxies, too small to see in any individual image, but detectable when millions of galaxy shapes are averaged together. A galaxy that is intrinsically round appears slightly elongated in the direction tangential to the lensing mass. Galaxies that are intrinsically elongated appear slightly more or less elongated depending on their orientation relative to the foreground structure. Individually, each distortion is lost in the noise of the galaxy's own shape. Collectively, they reveal the gravitational landscape of everything between us and the distant universe. It is a form of seeing that requires not sharpness but patience, not the single perfect observation, but the accumulation of millions of imperfect ones, each one adding a little more signal to a picture that only becomes clear when enough of them are brought together. It may be that some kinds of understanding share that quality, that the truest picture of a thing does not come from any single clear view, but from the patient accumulation of many partial ones, each imperfect, each limited, but together sufficient to reveal what no individual observation could. The light that forms an Einstein ring has travelled in many cases billions of years to reach the telescope. It was emitted by a galaxy that existed when the universe was young, passed by a galaxy that may not even exist in its current form by the time the light reaches its destination, and arrived shaped into a circle that would have been impossible without the precise chance alignment of everything along its path. It did not plan this. Nothing in the story of an Einstein ring involves intention or purpose. It is simply what happens when light travels far enough through a universe sufficiently structured and sufficiently full of mass. The beauty is a byproduct of physics. The ring is what the equations look like when you photograph them, and somehow that makes it more rather than less wonderful. The further back in time astronomers look, the more these tools of lensing and geometry become essential. Because the most distant galaxies, the ones that existed when the universe itself was barely old enough to have formed them, are also the faintest and the smallest. And the questions they raise about the history of everything are among the deepest that the science of galaxies has ever produced. The night carries us further back now toward the edge of what can be seen, and toward a question that has been quietly unsettling the standard picture of cosmic history for several years. The furthest thing we've ever seen is a galaxy, not a star, not a nebula, not the afterglow of some ancient explosion, though that too has been observed at extraordinary distances. A galaxy, a structured collection of stars and gas and dark matter already organized, already rotating, already doing what galaxies do, existing when the universe was less than 350 million years old. 350 million years sounds like a long time. In human terms, it is incomprehensible. It reaches back further than the first complex animals on Earth, further than the first continents, further than almost any geological record we can read. And yet in cosmic terms, 350 million years after the Big Bang is almost nothing. It is roughly 2.5% of the current age of the universe. The universe was by any reasonable measure an infant. The stars themselves had barely had time to form. The first generation of them, the enormous, brilliant, short-lived stars of the early cosmos, had only recently ignited, and in that infancy already there were galaxies. The instrument that brought these objects into view is unlike any telescope that came before it. Launched in the final days of the year 2021 and placed at a point in space roughly 1.5 million kilometers from Earth, the telescope that carries the name of a former administrator of the National Aeronautics and Space Administration observes the universe primarily in infrared light. This is not an incidental technical detail. It is the reason the telescope can see what it sees. The universe is expanding. Light from very distant objects, light that has been travelling for billions of years, is stretched by that expansion. The shorter wavelengths of visible light are pulled toward longer wavelengths, shifted into the infrared, into the warm glow frequencies that the human eye cannot detect, but that carefully designed instruments can read with extraordinary precision. The further away an object is, the more its light has been stretched, and the further into the infrared its signal falls. To see the most distant galaxies you need eyes built for infrared, and this telescope has them cooled to within a few degrees of absolute zero to reduce the thermal noise of the instrument itself, nestled behind a sunshield the size of a tennis court, positioned far enough from Earth that our planet's own infrared glow cannot contaminate the observations. The first images it returned showed galaxies at distances and redshifts that surprised even the astronomers who designed it. What was surprising was not simply that these early galaxies existed, it was how they looked. The standard model of cosmic structure formation, refined over decades of observation and simulation, predicted that the earliest galaxies should be small and irregular. In the young universe, the theory suggested structure had not had time to organize itself into large, coherent systems. The first galaxies should be compact, chaotic, rapidly forming stars, but not yet settled into the orderly, rotating structures we see in the nearby universe. Some of what the telescope found matched that expectation. There are early galaxies that are small and irregular and brilliantly active, blazing with star formation, at rates that make the current Milky Way seem almost idle by comparison, but there are others that should not be there. Galaxies that at redshifts corresponding to the first few 100 million years of cosmic history already appear massive, already structured, already containing hundreds of billions of solar masses worth of stars assembled into systems that look in some cases disconcertingly mature for their age. Researchers have found several of these objects now enough that they are no longer anomalies to be questioned individually, but a genuine statistical challenge to the models. The question is not whether they are real. The question is how they got so large so quickly. In the standard picture of how structure forms in the universe, small things form first. Dark matter collapses into small halos, galaxies form within those halos, and over billions of years mergers accumulate small galaxies into larger ones. It is a hierarchical process, patient and gradual, driven by the slow accumulation of gravitational influence. That process works well for the universe we can see nearby. The galaxies in our local environment, the ones whose histories we can partially reconstruct, are consistent with a picture of gradual growth over cosmic time. The Milky Way itself, as noted earlier in this night, shows the signatures of ancient mergers in its stellar populations, evidence of the accumulation that built it to its current size. But to assemble a galaxy containing hundreds of billions of solar masses of stars within the first few 100 million years of cosmic history requires either star formation rates far higher than anything observed in the nearby universe, or initial conditions in the early universe that allowed structure to form more quickly than the standard model predicts, or some combination of both, or something else that has not yet been clearly identified. Scientists are still exploring all of these possibilities with genuine openness. It may be that the very early universe was denser and more turbulent in ways that accelerated the collapse of gas into stars. It may be that the first generation of stars, the so-called population 3 stars, massive and brilliant and short-lived, enriched the surrounding gas with heavy elements much faster than current models assume, changing the cooling properties of the gas and allowing subsequent star formation to proceed more rapidly. It may also be that the models require revision in more fundamental ways, that our understanding of how dark matter halos form and grow in the very early universe is incomplete, that some process operating at high redshift is more efficient at building structure than the simulations currently capture. What the telescope has done more than answering questions is sharpen them. This is what good instruments do. They do not arrive and resolve everything. They arrive and reveal the next layer of what is not yet understood. Every answer they provide creates a more precise version of the question that follows. The galaxies at the edge of the observable universe are not a problem to be solved and set aside. They are an invitation to reconsider, to refine, to look more carefully at the assumptions embedded in the models, and ask which of them are firmly grounded and which are approximations that might not hold in the conditions of the very early cosmos. Evidence suggests that the models will be updated rather than overturned. The basic picture of a universe beginning in a hot, dense state, expanding and cooling, forming structure hierarchically under gravity, is robustly supported by independent lines of evidence from the cosmic microwave background, from the large-scale distribution of galaxies, from the abundances of light elements produced in the first minutes of cosmic time. These broad strokes are not in question. The details, though, the specific timing of when the first large galaxies appeared, the efficiency of star formation in the early universe, the role of the first black holes in shaping the first galaxies, these are all being actively revised in light of what the new telescope is finding. And the revision is happening not with anxiety but with the particular quiet excitement that comes when a field of science realizes it has more to learn than it thought. There is a temporal quality to observing very distant galaxies that deserves to be held for a moment. When the telescope detects light from a galaxy at the edge of the observable universe, that light was emitted roughly 13.5 billion years ago. The galaxy that emitted it no longer exists in that form. In the time the light has been travelling, the galaxy has continued to evolve, to merge with neighbours, to form and lose stars, to change, in ways we cannot observe because the more recent light has not yet had time to arrive. What we see is not the galaxy. It is a memory of the galaxy, a frozen record of how it appeared at one moment in the deep past. In this sense, the observable universe is a kind of archive. The further you look, the older the record. The edge of what is observable, the cosmic horizon beyond which no light has had time to reach us, is not a physical boundary but a temporal one. It is the distance that corresponds to the age of the universe. We cannot see beyond it, not because there is nothing there, but because the light from there has not finished its journey. Everything we see from the nearest star to the most distant galaxy is history. The universe does not show us its present. It shows us its past layer by layer at different depths of time, each observation a window into a different moment in a story that is still unfolding. It may be that sitting with this, really sitting with it without rushing to a conclusion or a metaphor, produces something that ordinary looking does not. A kind of temporal humility, an awareness that what we call the present is always a small local agreement between things close enough to exchange light, quickly embedded in a universe where the present is not a single moment, but a vast landscape of different moments, arriving from different distances simultaneously. The stars overhead tonight are the sky as it was. Some of those points of light no longer exist. Some have expanded into red giants, some have collapsed, some have simply burned out their end, predating the message that is still travelling toward us. We cannot know which ones. The news of their endings is still on its way. And somewhere out there at the very edge of what can be seen, those early galaxies continue their ancient existence in the record of their own light, holding a question about the first chapters of cosmic history that scientists are only now beginning to read clearly enough to understand. The mind, it seems, has been keeping something still and patient all along, because somewhere beneath the restlessness of daily thought, beneath the movement and noise of ordinary awareness, there is a quieter register, one that has always understood that most of what is real arrives slowly from far away and asks only that you be still enough to receive it. The universe has been sending its messages for billions of years. Some of them are only now reaching the instruments we have built to receive them, and some of what they tell us opens onto something that is not about galaxies at all, but about the spaces between them, and what those spaces, despite their apparent emptiness, actually contain. Between the galaxies there is almost nothing. Almost. That single qualifier carries more weight than it might seem, because the difference between nothing and almost nothing at the scale of the universe is not a small distinction. It is the difference between a void and a medium, between absence and presence so thin it barely registers, between a universe that is mostly empty and a universe that is everywhere in some sense full. The space between galaxies is not vacuum in the way that word is usually understood. It is not the clean, perfect absence of matter that the word suggests. It is something more subtle than that, and more interesting, and in ways that researchers are still carefully measuring more consequential than its near invisibility might imply. The most abundant component of the space between galaxies is gas, not cold gas, not the kind that forms clouds and collapses into stars. Hot gas, extraordinarily hot by ordinary standards, heated over billions of years by the shock waves of galaxy formation, by the jets of active black holes, by the release of gravitational energy as matter fell into the large-scale structures of the cosmic web. This gas, called the warm-hot intergalactic medium, sits at temperatures ranging from roughly 100,000 to 10 million degrees too hot to form molecules too diffuse to radiate efficiently, and too spread out to be easily detected by conventional means. For decades, this gas was primarily a theoretical prediction. The models of how baryonic matter, the ordinary protons and neutrons and electrons that make up everything we can touch, distributes itself throughout the universe, suggested that a large fraction of it should be in this warm-hot intergalactic phase. But detecting it proved difficult. The gas is so tenuous, containing perhaps 1 to 10 particles per cubic meter on average, that its signal is weak against the background of other sources. Evidence suggests that astronomers have now confirmed its presence through multiple techniques, including the absorption of ultraviolet and X-ray light from distant quasars, passing through filaments of this gas, and through its faint thermal imprint on the cosmic microwave background radiation. The missing baryons, as they came to be called, the ordinary matter that models predicted, but observations could not find, appear to reside largely in this nearly invisible, warm-hot medium threading the space between galaxies. The intergalactic medium is not uniform, it follows structure. The large-scale distribution of matter in the universe is not random. Gravity, acting over billions of years from the tiny density fluctuations present in the very early universe, has assembled matter into a vast network of filaments, sheets and nodes, the cosmic web described briefly in the opening hours of this night. The densest nodes, where multiple filaments intersect, host galaxy clusters, enormous concentrations of hundreds to thousands of galaxies embedded in deep gravitational wells. The filaments between them are narrower threads of somewhat higher density, containing galaxies and gas flowing along their length, and between the filaments occupying the majority of the volume of the universe are the voids. The voids are the closest thing in the observable universe to true emptiness. A typical cosmic void spans anywhere from a few tens to a few hundreds of millions of light-years across. Within that enormous volume, galaxy density drops to a fraction of the cosmic average. There are still some galaxies in voids scattered thinly through them, often smaller and more isolated than galaxies in denser environments. But most of the volume of a void contains almost no galaxies at all. What it does contain is the thinnest imaginable thread of the intergalactic medium. Gas at densities far below even the low average of the filaments. A handful of particles per cubic meter, drifting through an enormous space with no galaxy close enough to significantly alter their motion or their temperature. Researchers have found that galaxies in the outskirts of voids positioned on the edges where void meets filament show subtle differences from galaxies in denser environments. They tend to be slightly bluer, slightly more actively forming stars, slightly less likely to have been quenched by the environmental effects that suppress star formation in clusters. The void, for all its emptiness, is in some sense a gentler place to be a galaxy. Less disruption, less stripping of gas by neighbours, more isolation, and within that isolation more freedom to follow the galaxy's own internal evolution. The voids themselves are not static, they expand. As the universe grows and dark energy drives the accelerating expansion of space, the voids grow with it, their boundaries pushed outward as the matter on their edges is drawn into the surrounding filaments and sheets. The interior of a void becomes over time more and more empty as whatever sparse matter it contains is gradually evacuated toward the denser structures at its edges. It seems that this evacuation is one of the mechanisms that feeds the growth of galaxy clusters. Matter falling into voids from all directions compresses along filaments and collects at nodes, adding to the mass of clusters that are already among the most massive gravitationally bound structures in the universe. The voids feed the clusters the way rain falling on a hillside feeds the rivers at its base, not directly, not quickly, but persistently over billions of years. This flow of matter from voids through filaments into clusters is one of the large-scale dynamics of cosmic structure. Everything is in motion as discussed earlier. But the motions are not random. They follow the gravitational landscape of the cosmic web, draining from the underdense regions and pooling in the overdense ones, a slow rearrangement that will continue as long as gravity and dark energy jointly shape the evolution of the universe. Dark energy deserves a moment here, though what can be said about it honestly is less than what is usually said. It was inferred in the late 1990s from observations of distant supernovae, which appeared slightly dimmer than expected for their redshift, implying that the expansion of the universe is not slowing down under gravity, as had been generally assumed, but accelerating. Something is driving that acceleration. Something with a negative pressure in the language of physics, something that does not dilute as the universe expands but maintains a constant energy density, even as space grows. It has been called dark energy, which, like dark matter, is a name more for what it is not than for what it is. What we understand so far suggests that dark energy constitutes roughly 68% of the total energy content of the universe. Dark matter accounts for roughly 27%. Ordinary matter, everything that has ever been observed directly, every star, every galaxy, every atom of gas, every planet, every person accounts for roughly 5%. The universe is in its composition mostly things we do not understand. The 5% that we can see and measure and describe is in a sense the thin surface of something far larger and far more opaque. Scientists are still exploring the nature of dark energy with instruments of increasing precision, measuring the geometry of the universe through surveys of millions of galaxies, looking for deviations from the simplest model, a cosmological constant a fixed energy density of empty space that Albert Einstein introduced and then withdrew, and that the observations have somewhat ironically resurrected. Whether dark energy is truly constant or slowly changing over cosmic time is one of the most actively investigated questions in contemporary cosmology. There is a texture to the void when you sit with it long enough. Not a physical texture, nothing to feel against the skin, but a conceptual one, the sense of a space that is defined as much by what is not there as by what is. The void is the background against which the filaments and clusters become visible. Without the emptiness, there would be no structure to see. The galaxies arranged into their threads and walls and nodes only become recognizable as a pattern when you hold the void alongside them, when the contrast between dense and sparse makes the shape of the whole legible. In this sense, the emptiness is not separate from the structure. It is part of the structure. The shape of a void is the shape of the matter that is not inside it. The two define each other the way silence defines sound, the way the space between words makes language possible. The mind quietly registers something in this, that the parts of experience that seem most absent are sometimes the ones giving shape to everything else. Researchers have also found in the intergalactic medium of filaments and the outskirts of clusters the chemical fingerprints of stars that no longer exist. Stars over their lifetimes fuse hydrogen and helium into heavier elements, carbon-oxygen, silicon-iron, and all the others. When massive stars end their lives in supernova explosions, they scatter those heavy elements into the surrounding gas, enriching the interstellar medium with the products of nuclear fusion. In galaxies with strong outflows driven by the combined energy of many supernovae, or by the jets of an active black hole, this enriched gas can be expelled beyond the galaxy itself into the circumgalactic medium surrounding it, and in some cases further still into the intergalactic medium of the surrounding filament. Observations of absorption lines in the spectra of background quasars have detected carbon-oxygen and other heavy elements in gas far removed from any visible galaxy. These elements were made inside stars. They were processed through stellar interiors at temperatures of millions of degrees. They were expelled in the violence of stellar death, and they are now drifting quietly through the space between galaxies far from any source of new starlight, carrying in their atomic structure the record of the stellar lives that created them. The intergalactic medium is in this sense the universe's long memory, the residue of everything that has ever burned and ended and scattered its contents into the larger space. It is not empty. It is full of history written in wavelengths too faint for the eye, in densities too low for conventional measurement, in temperatures too extreme for ordinary instruments. But it is there. It has always been there, patient and diffuse, and threaded through the vast architecture of the cosmos, holding within its near-nothingness the accumulated record of everything that has come before. And when you step back far enough, when the scale becomes large enough that individual galaxies blur into points, and the filaments become visible as lines, and the voids open into their full enormous extent, the whole structure resolves into something that has no precedent in human experience. Something worth seeing in the slow hours of this night from just a little further away. Part moi mod dung structure, I drift reflection ket hope. Be expanding field but jau tukwan saat kudeve cosmic web morong rasu tuong jung, voi mangthan kin roi dan chuyan sang suin gamvei nanghia kwa ket nui tros kinen hangha, suong chuan bi cho pen quo, kwang hai nang hin by tram tu cho he moi mod put narration cham. Somewhere in the archive of modern astronomy there is an image that has stayed with researchers longer than most. It is not a photograph of a single dramatic object, not a supernova, not a black hole, not a collision of galaxies caught at the precise moment of maximum disturbance. It is something quieter than any of those things, and in its quietness somehow more arresting. It is a map a map of the observable universe at the larger scale assembled from the recorded positions of millions of galaxies, each one reduced to a single point of light, arranged across a field so vast that the familiar names of individual galaxies are meaningless at this resolution. The Milky Way, the Andromeda Galaxy, the Virgo cluster, all of it compressed into a region too small to find without a magnifying glass. What you see at this scale is the cosmic web, and what you notice looking at it for long enough is that it looks like something else entirely. The cosmic web is the largest structure in the observable universe. It is not a structure in the way a crystal is a structure or a snowflake or a building, things assembled deliberately or grown through a single repeating process into a regular recognizable form. It is a structure in a looser and more interesting sense. The emergent pattern of 1 billion years of gravitational physics acting on the tiny density fluctuations present in the very early universe, amplified over cosmic time into the vast network of filaments, Wool's nodes and voids that now spans the full extent of what we can observe. Researchers have found that the cosmic web has a characteristic scale, the typical distance between filaments, the typical size of voids, the typical separation of major nodes. These are not random. They reflect the properties of the early universe, the density of matter, the ratio of dark matter to ordinary matter, the temperature of the primordial plasma, all encoded in the geometry of the structure that gravity subsequently built from those initial conditions. In this sense, the cosmic web is a fossil, a structure that carries within its geometry the memory of conditions that existed in the first fraction of a second of cosmic history, before the first stars formed, before the first atoms in a universe so hot and dense that nothing we would recognize as matter yet existed in stable form. The web is the universe's earliest memory written at the largest possible scale. The resemblance that has captured the attention of both scientists and people who are not scientists, the one that appears in popular articles and in the quiet corners of certain conversations, is this. At the largest scale, the cosmic web looks remarkably like a human brain. Not perfectly, not in every detail, but in the statistical character of the structure, in the way nodes connect through filaments, in the way dense regions are linked to other dense regions, through threads of lower density, in the proportion of the volume occupied by empty space versus occupied space. The two structures share properties that are by any reasonable measure surprising. The resemblance was studied formally by a pair of researchers, a neuroscientist and an astrophysicist, who published a comparison of the two structures in the year 2020. They analyzed the cosmic web as mapped by galaxy surveys and the human cerebral cortex as imaged by electron microscopy, and found that the two networks share similar statistical properties in terms of how their nodes connect, how their complexity scales, how the information, or in the case of the universe, the matter distributes itself across the network. They were careful, as good scientists are, to note what this similarity does not mean. It does not mean the universe is a brain. It does not mean there is any functional connection between the two structures. It does not mean that consciousness operates at cosmic scales or that the universe is in any sense aware of itself. What it means more modestly, but perhaps more interestingly, is that similar physical laws acting under similar constraints can produce similar patterns at vastly different scales. The processes that led gravity to build filaments and nodes across billions of light years, and the processes that led biological evolution to build axons and synapses across centimeters of neural tissue, are utterly different in their mechanisms. And yet, the geometry they produced, the shape of the network that results, carries family resemblances that the mathematics of network theory can quantify. This is a phenomenon that appears throughout nature at many scales. Branching structures, for instance, appear in river deltas, in the veins of leaves, in the bronchial trees of lungs, in the dendritic arbors of neurons, in the fracture patterns of drying mud, in the distribution of lightning channels through air. Each instance arises from different physical or biological processes. Each is constrained by its own set of materials and forces and boundary conditions, and yet the branching pattern itself recurs with variations across all of them, because branching is an efficient solution to the problem of distributing something water-oxygen electrical signal through a volume using a connected network of paths. The cosmic web and the neural network of the human brain are both solving a version of this problem, though the something being distributed and the scale and the mechanism are completely different. Gravity distributes matter through the cosmic web over billions of years. Electrochemical signals distribute information through neural networks in milliseconds. The scales differ by a factor of roughly 10 to the 27th power, and yet the network geometry that results from each process carries measurable statistical similarities. It may be that there are only a limited number of ways to build an efficient connected network under the constraints of physics and geometry, that the solution space is smaller than the intuition suggests, that the cosmic web and the brain arrived at neighbouring points in that solution space, not because of any deep connection between them, but because the space of possible solutions was always constrained enough that diverse processes would sometimes converge on similar forms. There is a particular kind of wonder available in that idea. Not the wonder of hidden meaning or cosmic intention, something quieter than that. The wonder of discovering that physical law is precise enough and constrained enough that it narrows the space of possible forms down to something recognizable. That the universe is not infinitely varied in its structures but patterned in ways that reflect the underlying regularities of the physics that generates them. The cosmic web is the universe following its own rules at the largest available scale, and the brain is life following its own rules at the scale of a few centimeters. And the rules, while utterly different in their specifics, produce in the geometry of their networks something that rhymes. What the cosmic web also reveals when you look at it carefully is the history of the universe's information. The positions of galaxies today are not random. They reflect the positions of the dark matter halos that formed first, which reflect the density fluctuations that were present in the primordial plasma, which reflect the quantum fluctuations that were stretched to cosmic scales by the rapid expansion of the very early universe, which some cosmological models suggest occurred in a period called cosmic inflation, a fraction of a second after the beginning of everything. If inflation occurred as the leading models describe it, then the largest structures we can observe, the walls and voids and filaments of the cosmic web, spanning hundreds of millions of light years, are the amplified imprints of quantum events that occurred in a region smaller than an atom in a moment so brief it has no name in ordinary time, the smallest and the largest connected through a chain of physical consequence so long and so precise that tracing it from one end to the other requires the full apparatus of modern cosmology. And yet, the connection is real and verifiable and reflected in the statistical properties of the cosmic web in ways that observations have confirmed with increasing precision over the past several decades. Studies indicate that the pattern of fluctuations in the cosmic microwave background radiation, the faint thermal afterglow of the Big Bang detectable in every direction of the sky, matches the pattern of the large-scale distribution of galaxies in ways predicted by the inflation models. The early universe and the late universe are telling the same story in different languages at different scales, and the correspondence between them is one of the most remarkable consistency checks in the history of science. There is also what the web reveals about where we are within it. The Milky Way sits within a filament of the cosmic web part of the Laniakea supercluster, not at a node, not at the center of any particularly dense region, but along the length of a thread connecting larger structures on either side. We're in the geography of the cosmic web somewhere in between, not at the center of anything, not at the periphery of everything. Embedded in the fabric partway along one of its threads, surrounded by the warm hot intergalactic medium described in the previous section of this night, held within a dark matter halo moving with the general flow of matter toward the denser regions that gravity is slowly assembling. It is a very ordinary position by cosmic standards, and there is something deeply comfortable in that ordinariness. We're not special in our location. We're not at a privileged point in the structure. We're simply here in this particular filament, on this particular spiral arm, on this particular planet, looking out at the whole enormous pattern from one small, unremarkable position within it. The view from here is still astonishing. What we understand so far suggests that the cosmic web will continue to evolve. The voids will grow as dark energy drives the expansion of space and evacuates their interiors. The filaments will thin as matter drains from them into the increasingly massive clusters at their nodes. The clusters will grow slowly, accumulating the last infalling material before the accelerating expansion eventually isolates them from each other entirely, leaving each cluster as a gravitationally bound island in an expanding sea too far from its neighbors for any future light to bridge the distance. In the very far future, the observable universe from within any such isolated cluster will be smaller than what we can see today. The galaxies beyond the cluster will have receded beyond the cosmic horizon, their light never reaching us again, the web itself invisible, because its threads will have thinned beyond detection. What remains visible will be only the local concentration, a smaller and smaller window into what was once a much larger observable cosmos. But that future is incomprehensibly distant. On any scale relevant to a human life or a civilization or a geological era, the cosmic web is effectively eternal in its current form, stable and structured and vast, holding its pattern of filaments and voids across scales that dwarf everything we have ever considered. And somewhere in all of that structure, in all those filaments and nodes and the vast quiet spaces between them, there are galaxies that are gently, quietly wrong, that do not rotate as predicted, that stopped making stars long ago, that grew too quickly, that contain almost no dark matter, that bend light into perfect rings, that sent their first photons before the universe had learned how to make them so large so fast. Each one a small variation on the pattern, each one a place where the rules applied with perfect consistency produce something unexpected. And in those unexpected places the universe reveals itself most clearly, not as a system that follows simple laws mechanically, but as something richer. Something that generates within its own consistency an endless variety of forms, each one following the physics exactly, each one arriving somewhere no one quite predicted. The cosmic web holds all of it. Every anomalous galaxy, every dark matter halo, every gravitational lens, every red and dead elliptical, every pale ultra-diffuse ghost, every overmassive black hole sitting at the center of its host, like a stone that has grown larger than the room around it. All of it connected, all of it woven into the same enormous fabric, all of it in the end quiet. And somewhere in that quietness, after such a long journey through the strange and the vast and the gently inexplicable, the night itself has something to offer that no telescope has yet been built to measure. Something that has been here all along, patient and unhurried, waiting for the moment when the mind finally slows enough to notice it. We have never seen dark matter. Not once. Not in any laboratory, not through any instrument, not in any observation that captures it directly, rather than inferring its presence from what surrounds it. It shapes the rotation of every galaxy we have ever measured. It bends light. It holds the cosmic web together. It outweighs all visible matter by a factor of 5 to 1. and it has never in the entire history of physics revealed itself as anything other than an absence that behaves like a presence. There is something in that which the science alone cannot fully contain. The history of astronomy is in some sense a history of discovering that things we could not see were nevertheless real. Neptune was predicted from the gravitational perturbations of Uranus before anyone had looked in the right part of the sky to find it. The existence of atoms was inferred from the behavior of gases long before any instrument could resolve them individually. Black holes were mathematical solutions to Einstein's equations for decades before the first observational evidence confirmed that they exist in nature. And dark matter joins that lineage the long tradition of science, learning to trust the logic of what is implied over the comfort of what is directly seen. What makes dark matter different from all of these is that the others eventually yielded. Neptune was found, atoms were imaged, black holes were photographed. Dark matter, after decades of dedicated searching, with detectors buried deep underground to shield them from cosmic ray interference, with particle accelerators, generating the highest energy collisions ever achieved by human technology, with astronomical surveys of unprecedented scope and precision has not. Scientists are still exploring every viable hypothesis. The candidate particles have narrowed and shifted over time. Some of the most popular early candidates have been ruled out by the sensitivity of the detectors that searched for them. Others remain viable. New theoretical frameworks propose different kinds of dark matter, lighter or heavier, more weakly, or more strongly interacting, perhaps not a single particle, but a whole sector of particles interacting only among themselves and with ordinary matter through gravity alone. The honest position held by most researchers in the field is that we do not yet know what dark matter is. We know it is there. We know a great deal about what it does. We do not know what it is made of. And then there is the matter of why the universe is the way it is at all. The cosmic web, the filaments and voids and clusters, the specific pattern of structure visible in the galaxy surveys emerge from tiny fluctuations in the density of the early universe. These fluctuations imprinted in the first tiny fraction of a second, after the Big Bang, were quantum in origin. They were the amplified traces of quantum uncertainty raised to cosmic scales by a period of extraordinarily rapid expansion in the very earliest moments of cosmic history, a process called inflation. The specific pattern of those fluctuations, their amplitude and their distribution across scales, determined which regions of the universe would eventually collapse into structures and which would expand into voids. The cosmic web we inhabit is in this sense the grown form of quantum noise. The largest structures in the observable universe trace their origins to the smallest possible scales of physical reality. Researchers have found that the pattern of fluctuations measured in the cosmic microwave background, the oldest light in the universe, the afterglow of the hot early cosmos still detectable today as a faint glow of microwave radiation arriving equally from all directions, matches the predictions of inflationary models with remarkable precision. The specific peaks and troughs in that pattern encode the geometry of the universe, its total energy content, the relative proportions of dark matter and dark energy and ordinary matter, the history of how structure formed. It seems that everything visible in the universe today, every galaxy, every cluster, every filament, every void, every star and planet and molecule and person, is the deterministic consequence of conditions set in the first moments of cosmic time, amplified through gravity and chemistry and biology across 14 billion years of subsequent history. That is either the most humbling thing imaginable or the most grounding, depending on how you hold it. The universe did not have to be this way. The fluctuations could have had different amplitudes. The proportions of matter and energy could have been different. The laws of physics could have taken different forms. In the vast space of possible universes that the mathematics allows, the specific one we inhabit, the one with galaxies of this kind and stars of this kind and planets and chemistry and the conditions for life, is one particular outcome of one particular set of initial conditions. Why those conditions? Why these laws? Why anything at all rather than nothing? These are questions that physics approaches carefully with the awareness that some of them may lie outside what observation can answer. They are not dismissed. They are held openly as some of the deepest questions that a mind capable of asking them can formulate. What we understand so far suggests that the universe is not arbitrary in its structure. The laws of physics are not random. The constants of nature, the strength of gravity, the charge of the electron, the mass of the proton sit within ranges that permit the complexity we observe. Whether this reflects a deeper necessity, a multiverse of possibilities of which we inhabit one, or something else entirely, is genuinely open. Scientists carry the question honestly, without forcing it toward a premature resolution. There is practice in certain kinds of attentive looking that involves not the accumulation of more detail but the gradual release of it. You begin by looking carefully. You notice the shape of a thing, its edges, its texture, the way light moves across it. And then slowly you allow the focus to soften. Not to stop looking, but to look differently, to let the specific details blur slightly, and the overall quality of the thing become more present. What you lose in precision you gain in a different kind of knowing. Astronomers who have spent careers studying galaxies describe something like this. The accumulated detail, the rotation curves and redshifts and merger histories and black hole masses and stellar populations becomes at some point not a collection of separate facts but a single complex impression of something. The galaxy as a whole, the way it has moved through time, the way it belongs to a larger structure that belongs to a larger structure still. Evidence suggests that this kind of knowing, the kind that comes after a long time of careful looking, is qualitatively different from the knowing that comes at the beginning. It is not less rigorous. It is not less scientific. It is the same facts held differently, with more of the connections between them visible, more of the context present, more of the uncertainty acknowledged and rested in rather than struggled against. The galaxies that open this night, the ones with their anomalous rotation curves, their missing dark matter, their overmassive black holes, their unexpected maturity in the early universe, their pale ghostly diffuseness, their quenched silence, are all in the end variations on a single theme. The universe does not fit perfectly into any model we've built for it, not because the models are wrong in their foundations, but because the universe is richer than any model, more varied, more locally particular, more full of specific histories that no general principle fully anticipates. Every galaxy has lived its own life, been shaped by its own sequence of interactions and conditions, arrived at its present state through a path that no other galaxy has taken in exactly the same way, and we, looking at them from this small planet in this average spiral arm of this unremarkable galaxy, on the edge of the Laniakea supercluster, are trying to read those histories from the light that has travelled to us across distances and times that exceed all intuition. We're doing it slowly, imperfectly, with growing precision and genuine wonder. That seems like enough. For a universe that has been here 14 billion years and will be here for far longer than that, the pace of understanding does not need to be urgent. Wind down begins here. The night is deep now. The questions are still there somewhere, but they have grown quieter, less insistent, more like the background of things than the foreground. The galaxies are still turning, slowly as they always have, the outer stars keeping their impossible speed. The dark matter halos extending far beyond what any photograph can show. The pale, enormous, ultra-diffuse galaxies are drifting through their clusters, almost empty, still held. The ancient light from the edge of the observable universe is still travelling, still arriving. 13.5 billion years in transit and still coming. The great attractor is still pulling, gently, persistently, everything in this corner of the cosmos moving toward it at a speed no individual can feel. The space between galaxies holds its thin, warm gas, its scattered heavy elements, the residue of stars that ended before the Earth existed. The cosmic web holds its shape, filaments and voids. The universe breathing in and out over timescales too long for any metaphor. Somewhere an Einstein ring is forming. Light from a galaxy, billions of years old, bent around a mass it will never know, arriving at an instrument that was not built until long after the light began its journey. Somewhere a galaxy is being quenched, its last stars forming now without knowing they are the last. Somewhere two black holes are spiraling together, the final moments of a merger that began before the solar system existed. Somewhere in a very young part of the universe, a galaxy is assembling itself from gas and dark matter, the first stars igniting, the first heavy elements forming, the first trace of structure in what was moments before only a density fluctuation, a quantum whisper amplified to cosmic scale. All of this is happening now, at this moment, in the universe that surrounds this small planet, invisible mostly, silent entirely, present. You are inside it. Not metaphorically. You are embedded in the cosmic web. You're made of elements forged in stellar interiors. The iron in your blood was synthesized in a star that exploded before the sun formed. The calcium in your bones was scattered by supernova shockwaves across interstellar space, before gravity gathered it eventually into the cloud that became the solar system. You're not separate from what we've been talking about tonight. You're a local arrangement of it. A small, temporary, conscious local arrangement. And that arrangement is resting now. The breath slows. The thoughts grow softer. The distance between the stars and the distance between synapses becomes for a moment the same kind of distance. Vast and somehow intimate. Something out there is wrong in all the ways we explored tonight. And something out there is also quietly, continuously exactly as it should be. The galaxies turn, the dark matter holds, the light travels, and somewhere between the knowing and the not knowing, there is a place where the mind can simply rest. You're already there.